Now we've seen chemical formulas. Chemical formulas show how many atoms of each element we have in our chemical or our compound. We have ionic chemical formulas, and we usually call those formula units. We have covalent compounds, and we usually call those molecular units or molecular formulas. Remember that an ionic compound is made up of a metal and a nonmetal, and they gain and lose electrons in order to form ions and then combine through an electrostatic force in order to form an ionic compound. We also have covalent compounds, and they're made up of one or more nonmetals joined together, and it's two or more atoms of nonmetals, and they're joined together by sharing their valence electrons. When they are covalent and sharing those electrons, then we usually call them molecules. We can analyze the mass of some of these formulas by using the atomic mass on the periodic table and coming up with the formula mass. So if we have a compound like this is C6H6, and specifically I'm looking at the benzene ring. Now a benzene ring is a special organic molecule, and it's shown like this. You've probably seen it at least once. It's a hexagon, and it has alternating double bonds. We're going to get into that in the next module. But this is benzene. Now benzene is made up of 6 carbons and 6 hydrogen atoms, and that makes one molecule. So if we go, just to briefly review, if we go to calculate our formula mass here, we look up the atomic mass of each of our constituent elements, and we multiply it by the subscript number, which tells us how many of each of those elements we have, and we find the molar mass contribution of each of those elements. And when we add that together, we get the molecular mass, the molar mass, and for benzene that happens to be 78.12 grams per mole. Now we can describe benzene by describing its percent mass. And in order to do that, this is actually called percent composition. So in order to do that, we take the amount that each element is going to contribute. So here, if I'm looking at percent carbon, I take the amount that carbon contributes to the molar mass, which is the 72.06 that I just highlighted over there, and I divide it by the molar mass, so 78.12 grams per mole, and then I'm going to multiply that by 100. So plug that into the calculator. You should get something that rounds to 92.24%. Now, because benzene is the only other element in benzene is hydrogen, we could just take 100 and subtract 92.24% and find the percent hydrogen, but we really should go through the steps. So we take the mass that hydrogen contributes to the molecular formula, divide it by the molecular formula, multiply that by 100, and I happen to get a percent mass of 7.76%. So how could you use this in a problem? Well, you may see something like if we have a sample, and that sample has a mass of 12.04 grams. We know that this sample contains carbon, hydrogen, and nitrogen. When it is destroyed, I don't know, when it is burnt up, when it is, maybe it's a combustion analysis, but regardless, the analysis yields 7.34 grams of carbon, 1.85 grams of hydrogen, and 2.85 grams of nitrogen. What are the percent composition values for each of those elements? Well, remember, our percent composition is going to be comprised of the percent of the element divided by the mass of the compound. I said percent of the element. It's the mass of the element in the compound itself, divided by the mass of the compound or the molecule, so the formula, and all of that multiplied by 100. I seem to have run out of room here, so if I put my 100 multiplied by that. Well, if we have the masses of the elements here, how are we going to find the mass, the formula mass of this compound? Well, we're told that it's 12.04. So if I divide each of these by 12.04 and then multiply by 100, then I will get the percent composition of each of these elements. So for carbon, I get 61.0%. For hydrogen, I get 15.4%. And for nitrogen, I get 23.7%. Well, what if instead of the chemical formula, we're given something like this? We're going to be drawing molecules in the next module. So this is kind of a preview. And what this shows is that we have 2 atoms of carbon and we have 2 atoms of hydrogen, and they're bonded together. This is a covalent molecule. So we have 2 carbon and we have 2 hydrogen. Now here we need to find what is the formula mass. So if we're going to calculate the percent composition of carbon and the percent composition of hydrogen, we need to calculate how much mass each of these elements lends to the molecule, and we need to calculate the molecular mass. So because we have 2 carbons, and carbon on the periodic table has a mass of 12.01, then carbon brings 24.02 grams per mole mass to the molecule. Hydrogen is 1.01. So because we have 2, it brings 2.02 grams per mole. So adding this together, the formula mass is then 26.04 grams per mole. Now we have all of the data we need in order to calculate the percent composition. So the percent carbon of this molecule is 24.02. I'm going to leave the units off for now, divided by 26.04. Multiply that by 100, and I get 92.24%. For hydrogen, I have 2.02 grams divided by 26.04, so that's the mass of hydrogen in the molecule divided by the molecular mass times 100, and I get 7.76%. Now I'm going to scroll up real quick, because when we did benzene, I want you to look at these values. See, the percent hydrogen is 7.76 and the percent carbon is 92.24. So how can the percent compositions be the same? Or if I have benzene, which is a very different molecule, when it's C6H6. And the answer to that is because they have the same empirical formula. The empirical formula is a formula that gives the smallest whole number proportion, but not the actual number of elements. So if you can take C2H2 and divide both of those subscripts by 2, you end up with CH. So CH times 2 is C2H2. If you divide the benzene formula by 6, our multiplier is 6. So you see we have the same empirical formula. So if we're given the masses of elements in a compound, we can determine the empirical formula by converting those to moles and comparing. Now, up until this point with this particular video, we have been using grams. 9 times out of 10 in my class, when you see grams, you should be converting it to moles. What we just did with percent mass is one of the times where you need to keep it as grams. So now what we're going to do is we're going to have a sample, and that sample is going to have iron, and we're going to find that it has 34.97 grams of iron. But it's also going to have oxygen, 15.03 grams. I should probably write that a little further down. So 15 0.03 grams of oxygen. So what is the empirical formula? In order to find that, we need to convert these grams into moles. So we need to use the atomic mass on the periodic table. So for iron, that's 55.85. And remember, our grams of iron need to cancel with grams of iron. We're left with moles of iron. And I get I'm going to use 4 significant figures, 6261. And that's moles of iron. Now I'm using 4 significant figures because my measured quantity here had 4 significant figures. So for oxygen, 1 mole of oxygen is 16.00 grams of oxygen. Again, making sure our grams of oxygen cancel with grams of oxygen. And I get a value of 0.9394 moles of oxygen. Now, it's tempting to round these numbers and call it done, but that is incorrect. What we need to do is find the ratio and compare. So what I'm going to do first is called making the pseudo-empirical formula. I'm going to use the values I'm given. Now, I know writing an empirical formula as well as a molecular formula, I need to have whole numbers. These are not whole numbers, but we're going to make them whole numbers by taking the smaller value and dividing both of these molar values by this smaller value. That means one element becomes 1. And I'm going to write the 1 here even though we usually leave it off. Now 0.9394 divided by 0.6261, I get 1.5. Now I need to point out that it's very important you don't round here unless you've got like 0.99 or 0.01, something very, very close to a whole number. You may need to review your decimals for common fractions. When we have a 0.5, I'm going to take this back a step and I'm going to make my 1.5 into an improper fraction. So I have 3 halves. So in order to get rid of my denominator now, I'm going to multiply both of these subscripts by 2. So if I multiply it by 2, I end up with Fe2O3, and that is my empirical formula. It's the smallest whole number ratio of elements based on the moles of the elements in my sample. Another way you may see a problem like this is if you're told you have something and it has 27.29% of an element. In this case, we're going to use carbon. And it has been shown to have 72.71% oxygen. What is the empirical formula? When you have percent, it's easy to say, since a percent is per 100, it's easy to say that, well, if my sample was 100 grams, then it would be 27.29 grams of carbon. And likewise, we would have 72.71 grams of oxygen. So when you have a percent, you can make that leap. Since it's per 100, if I have a 100 gram sample, that means my percent value can turn into grams of element. So now I'm going to convert those grams of element into moles of element by using the atomic mass from the periodic table. So I get 2.27 moles, not grams, moles of carbon. And with oxygen, I get 4.54 moles of oxygen. Now we take the same steps. We're going to write that pseudo-empirical formula. So 2.27, O gets 4.54. Now I'm going to divide both of these subscripts by the smaller molar value. And my C becomes 1, and oxygen becomes 2. Now this is okay, because what I get in my calculator is actually 2.026785, and it continues. But because I have this 0 and a very small number here, I can feel fairly confident rounding that into its whole number. In order to take an empirical formula and make a molecular formula, we need to know what its multiplier is. In the previous example, I showed you acetylene and I showed you benzene, and I gave it a number times the empirical formula. So once we have the empirical formula, we need to find this multiplier value, and that multiplier is going to be different depending on what our molecular formula is. So in order to find that multiplier, we need to be able to compare the mass of our empirical formula and the mass of our molecular formula. So let's do this example. If we have a sample and it contains 74.02% carbon, it contains 8.710% hydrogen, and 17.27% nitrogen. Then what is the molecular formula if we're told, and I'm going to write this little tidbit of information over here because we'll need it later, if 40.57 grams of this sample is 0.2500 moles. We need to find the molecular formula. Well, building on what we did in the last example, if we take our percent values and we turn them into grams, now we will calculate how many moles of each element we have. We're going to use the atomic mass found on the periodic table. .163 moles of carbon, 8.624 moles of hydrogen, and 1.233 moles of nitrogen. So I take my percent, I make it into grams, then I calculate how many moles of each element I have. Now I'm going to make that pseudo-empirical formula, CHN. And I have 6.163, I have 8.624, and then nitrogen is the smallest at 1.233. I divide each of my subscripts by 1.233 in order to get the empirical formula, and I get a C5H7N. Now this 5 in my calculator, this was 4.998. I'm fairly confident rounding that up. And my H was 6.99. Again, very confident in rounding that into the nearest whole number. So now I have my empirical formula, but I don't know my molecular formula. In order to find the molecular formula, I'm going to write this equation out one more time. So my molecular formula is going to be equal to some multiplier times the empirical formula. Well, what if these were the molar masses? So the empirical molar mass and the molecular molar mass. Then finding this unknown multiplier would be much easier. So the empirical molar mass we can work out fairly simply. We know we have 5 carbons, we have 7 hydrogens, and 1 nitrogen. So for the empirical molar mass, I get a value of 81.129 grams per mole. So I'm going to come over here and I'm going to start filling in my chart. So the number, I don't know. This is the multiplier I'm looking for. But the empirical molar mass, I have 81.129. I'm going to leave the units off for now, because they will cancel out. But how do I know the molecular molar mass? Well, that's going to take using these values here, because the molecular molar mass, remember the molar mass is going to be grams per mole. I'm given a mass, and that's 40.57 grams that I am told is 0.2500 moles. So when I do this division, 40.57 divided by 0.2500, I get that this is 162.28 grams per mole. So now I can divide both sides by 81.129 in order to get that multiplier by itself. So that multiplier ends up being 2. Now because that multiplier is 2, then I can take my empirical formula. I'm going to multiply it by 2, and what that means is I'm going to multiply each of my subscripts by 2. So C10, H14, N2 is my molecular formula. So we can go from the percent of each element into our molecular formula. Now this happens to be nicotine.